Welcome to Analytics Mastery Academy. My name is Kunal. Welcome to topic 4 of the Statistics Fundamental series. We have covered the tools, descriptive statistics, probability, and the normal distribution. Now we tackle the central problem of statistics. We want to know about populations, but we can only measure samples. In this video, we will explore sampling distributions, the key to understanding why larger samples are more reliable and how to estimate population parameters from samples. This is where statistics becomes powerful. So let's begin. Now let's start with what is population and what is sample. So let me start with fundamental distinction that underlies all the statistical inference. We have a population, all members of a group we are interested in, every voter in a country, every customer of a company, every student in a school. Populations are usually too large to measure completely. And then we have a sample, a subset of population we can actually measure. A poll of 1,000 voters, a survey of 500 customers, a test for 100 students. Here is a practical reality. In most real-world situations, measuring the entire population is impossible, impractical, and prohibitively expensive. A presidential poll can't interview 150 million people, right? A company can't survey every customer, and a manufacturer can't test every unit. So we measure a sample and use it to estimate the population characteristics. The population parameters we are interested in are mu, which is the mean, and sigma, that is the standard deviation. From our sample, we calculate the statistics, x bar, which is the sample mean, and s, which is the sample standard deviation. Now the critical question is, how reliable is our sample estimate? And that's what the sampling distributions help us to answer. Now, why sampling matters, right? So in my experience, understanding why sampling works is essential to understanding why larger samples are better. First, we can't measure entire population. With rare exceptions, populations are too large to measure completely. Trying to measure everyone would take forever and cost a lot of money. Second, sampling gives us workable estimates. Instead of surveying everyone, we survey a representative sample and use it to estimate population characteristics. This is pragmatic as well as practical. Third, the central limit theorem guarantees that our sampling approach is mathematically sound. The sample means we calculate will follow a normal distribution even if the population doesn't follow normal. The theoretical foundation is very powerful. Fourth, understanding the sampling variability explains why larger samples are more reliable, not through intuition, but through mathematics. The spread of sample means decreases predictably with the sample size. Fifth, sampling distributions form the foundation for hypothesis testing and confidence intervals. Everything we do with statistics relies on understanding how sample statistics behave across repeated samples. So now let's talk about what is a sample distribution. Now let me introduce the concept that ties everything together, which is the sampling distribution. Imagine this scenario, we have a population, we take a random sample of size n and we calculate its mean. We record this number, then we take another random sample of the same size n and we calculate its mean. We record this second mean as well. We keep doing this 1,000 number of times, taking samples, calculating means and recording them. Now we plot all these sample means. The distribution that we get, that's your sampling distribution of the mean. Here is what is remarkable about this, right? This sampling distribution has very specific properties. It is centered at the population mean and it's approximately normal shaped. Remember, central limit theorem. And its spread depends on both the population standard deviation and the sample size. The sampling distribution tells us if we took repeated samples, here is how much sample means would vary. And this is a very crucial information. Without sampling distributions, we could not do statistical inference. With them, we can calculate how confident we should be in our sample estimates. Now let's revise the central limit theorem. We mentioned central limit theorem before, but it's so crucial that I want to revisit it in the context of the sampling distributions. The central limit theorem says this: regardless of what distribution your population follows, the distribution of sample means is approximately normal, and this becomes increasingly true as sample size increases. Let me emphasize this. It doesn't matter if your population data is skewed, bimodal, uniform, or some weirdly shaped. The means of your samples will be approximately normal. This is the most powerful theorems in the statistics because it justifies our use of normal distribution in hypothesis testing regardless of the underlying population. For sampling distributions, central limit theorem tells us this. First, the sampling distribution of the mean is centered at around mu. The sample means on average equal to the population mean. Second, sampling distribution is approximately normal. So we can use Z-scores and 68, 95, 99.7 rule for sampling distributions. Third, the spread of the sampling distribution depends on the population standard deviation and sample size. Mathematically, that's the standard error formula we will discuss next. This is why sampling works and this is why statistics is possible. So standard error is the single most important concept for understanding sampling distributions. Standard error measures how much sample means vary from the sample to sample. It's the standard deviation of the sampling distribution. The formula is elegant. So it is nothing but the formula on the screen, right? Where sigma is the population standard deviation and n is the sample size. Let me unpack this formula because this tells us something very profound. The standard error equals the population standard deviation divided by square root of the sample size. What does this mean practically? So if you have a population standard deviation of 10 with a sample size of 1, the standard error will be 10 by square root of 1, which is 10. With a sample size of 4, the standard error will be 10 by square root of 4, which will be 10 by 2, which is 5. And with a sample size of 100, 10 divided by square root of 100, which is 10 by 10 is equal to 1. Notice, as we increase the sample size, the sample standard error comes down, right? Because of the root n, which means that you get diminishing returns actually. This explains everything about sampling. Larger samples gives you more precise estimates, but not in a one-on-one way, right? To cut the standard error in half, you need 4 times the sample size. To cut it to the half again, you need 4 times of that, right? So this mathematical relationship is why sample size planning is so important. You can't just arbitrarily pick any sample size. You need to understand the diminishing returns. Now here is a standard error example. Let me make a standard error concrete with a real example, right? Suppose you are studying human height. From the census data, you know the population standard deviation is 3 inches. So you want to estimate the population mean. So if you take the sample of 25 people, the standard error comes out to be 0.6 inches. If you take a sample of 100 people, it comes out to be 0.3 inches. And if you take a sample of 400 people, it comes out to be 0.15 inches. This is exactly why large surveys cost so much. Going from 1,000 samples to 4,000 samples costs 4 times as much, but you get only double the precision. Many researchers find a sweet spot where cost and precision balance may be somewhere around 1,000 to 2,000 responses. Understanding standard error helps you design your studies efficiently. Now, let me summarize the key properties of the sampling distribution of the mean. The sampling distribution is centered at mu, the population mean, and the sample means cluster around the true population value. Talking about the shape, the sampling distribution is approximately normal. This is the promise of the central limit theorem. Regardless of the original population shape, the sample mean forms a bell curve. Now talking about the spread, the standard deviation of the sampling distribution is the standard error, right? So standard error is nothing but standard deviation divided by square root of the sample size. This measures how much sample means vary. Effect of sample size, right? So larger n shrinks the sampling distribution. So distribution becomes taller and narrower, and the sample means cluster tightly around that population mean, mu. So what is the practical rule? About 95% of the sample means fall within the population mean plus or minus 2 standard errors. This comes directly from the 68, 95, 99.7% rule that we applied when we studied the normal distribution. These properties combine to show why statistics works, right? Our sample is our best estimate. The standard error tells us our margin of error. The normal shape lets us calculate probabilities and confidence levels. Now, let's talk about sample size and precision. One of the most important insights in statistics is doubling sample size doesn't double precision. Because standard error involves root n and not n, there is a square root relationship, right? Let me show the practical implications. To double the precision, you need 4 times the sample size. To triple the precision, you need 9 times the sample size. To cut the standard error 1 by 10, you need 100 times the sample size. So this has huge implications on the survey design, right? So improving from 400 to 1600 respondents doubles the precision, but it will also cost 4 times more. Is that actually worth it? Well, it depends on your needs. Most national surveys settle at around 1000 to 2000 respondents as the sweet spot, right? Smaller is cheaper but noisier. Larger is more precise but expensive. The mathematical relationship should inform all your decisions about sample size planning. Now, talking about estimating population mean, right? Now we kind of bring it all together. How do we use sampling distribution to estimate population parameters? Here is the logic. Our sample mean is our base estimate of the population mean. We actually in reality don't know the mu, which is the population mean. So we use our sample mean as our estimate. But how good is that estimate, right? That is what the standard error tells us. The standard error indicates how far is our sample mean typically from our population mean, which is the mu. Using the sample distribution, remember that 95% of the sample means will fall within mu plus or minus 2 standard error. This is the, again, 68, 95, 99.7 rule applied to the sampling distributions. Flipping this logic, if 95% of the sample means fall within mu plus or minus 2 standard errors, then we can be 95% confident that our mu will fall within sample mean plus or minus 2 standard errors. So a practical example, if your sample mean is 100 and standard error is 5, we are 95% confident that the true population mean will be between 90 and 110. This logic creates confidence intervals, which we will cover in detail in the next topic. For now, understand that sampling distribution gives us the precision of our estimates. They quantify the margin of error. This is why statistics works and why larger samples are more reliable. Here is a practical example. I'm not going to go through very deep in it, but this is actually how the statistics actually works in the real world, right? We take samples, calculate sample statistics, use sampling distributions to quantify precision and make estimates about the population. And this actually shows why the sample size actually matters. Now, here are some common misconceptions, right? Before moving on, we will address them. Misconception number 1, a bigger sample is always gives the right answer. Wrong. A bigger sample helps if it's a proper random sample, right? Bias sampling methods won't improve with the size. Misconception number 2, sampling distribution is the distribution of the raw data. Wrong. Sampling distribution is the distribution of the sample statistics like means across the repeated sample. It's not the same as the data distribution. Misconception number 3, standard error and standard deviation are the same thing. Again, wrong. Standard deviations measures the spread in the raw data. Standard error measures the spread of the sample statistics. They are very different. Misconception number 4, standard error is equal to sigma by n. Again, wrong. It is standard error is equal to sigma by root n. The square root is critical and it changes everything. We saw it earlier, right? Misconception number 5, we need to know the population distribution shape before using the sampling distributions. Again, wrong. We have central limit theorem, right, which can handle this. Even if population is wildly non-normal, the sample distribution of the mean is approximately normal. Understanding sampling distributions means cleaning up all these misconceptions. They are fundamental to getting statistics right. Now let's talk about the connection of sampling distribution and hypothesis testing. Sampling distributions are the foundation for hypothesis testing, which we will cover in detail in the next topic. Here is how hypothesis testing uses sampling distributions. Step 1, assume the null hypothesis is true. We assume the population means equals some specific value. Then we ask in the step 2, what's the sampling distribution under this assumption? If the null is true, the sample means should follow a particular normal distribution. In step 3, we look at the actual sample mean. Does it fall where we would expect it if the null were true, or is it in the extreme tail of the distribution? In step 4, we calculate the probability, the p-value. How likely is our observed sample mean if the null hypothesis is true? We measure far from expected in units of the standard error. Step 5, we make a decision if p-value is less than the threshold, typically 0.05, the result is too unlikely under the null, we reject the null hypothesis. Hypothesis testing is essentially asking, is our sample mean so far from what the null predicts that we should doubt the null hypothesis? Sampling distribution tells us exactly how to quantify the far using standard errors. Now, here are the key takeaways from this topic. Sampling distribution describe how sample statistics vary. Central limit theorem ensures sampling distributions are approximately normal. Standard error measures sampling precision. Larger samples reduce standard error by a factor of root n and not n. We use sampling distributions to estimate population parameters with known precision. And finally, these concepts power hypothesis testing and confidence intervals. Master sampling distributions and you have mastered the bridge between samples and populations. You understand why statistics works. Thank you for working through this sampling distributions section with me. This is where the real power of statistics emerges. In the next video, we tackle hypothesis testing, putting everything we have learned to use in making actual statistical decisions. If you have found this valuable, please like, subscribe, and comment. I read everything and appreciate your feedback. See you in the next one. Thank you.